Back in 2017, a single research paper came out and just completely flipped the script on artificial intelligence. The title itself was this incredibly bold claim: attention is all you need. Today, we're going to pull apart the transformer architecture that paper introduced and really get to the bottom of why it became the engine for the AI revolution we see all around us. So before the transformer came along, if you were working with sequential data, like language, the undisputed champions were recurrent neural networks, or RNNs. For anything from machine translation to generating text, they were absolutely the gold standard.
But RNNs had this one major weakness, kind of baked right into their DNA. They had to process information one piece at a time, just like reading a sentence word by word. And this created a massive fundamental bottleneck. You couldn't just throw more computing power at it to go faster. The process itself was the slow part.
And then this paper drops a totally new idea on the world: the transformer. And it did something radical. It threw out that step-by-step recurrence completely. Instead of going word by word, it proposed a model that could look at the entire sentence all at once, using this powerful mechanism called attention. Okay, so let's dive in and really see how the transformer manages to break free from that sequential chain. We're going to start peeling back the layers to see what truly makes this thing tick. The absolute core innovation here is self-attention. And to understand it, we really just need to get our heads around three concepts: queries, keys, and values. These are the tools the model uses to figure out for any given word how important all the other words in the sentence are. Think of it like this. For a word like it in a sentence, the model has to figure out what it actually refers to. Self-attention lets the model look at the whole sentence and calculate scores connecting it to every other word, finding the most likely answer. And it does this by creating three special vectors for every single word: a query, a key, and a value. So the fundamental unit, the real engine room of this whole operation, is what you see there on the left: scaled dot product attention. This is what drives the whole process. So let's break down exactly what's happening inside that little box. This slide lays out what is honestly a really elegant four-step process. First, for the word we're focusing on, the model takes its query vector and multiplies it against the key vector of every other word in the sequence. This gives you a raw score of how relevant they are to each other. Second, it scales those scores down just to keep the math stable during training. Third, a function called softmax turns those scores into probabilities, basically attention weights that all add up to 1. And finally, it multiplies those weights by the value vectors to create the output, a brand new context-rich version of our original word. So that's how one attention mechanism works. But the paper's authors realize that looking at a sentence in just one way isn't really enough to capture all the complexity of human language. And this brings us to the next level: multi-head attention. And that's a fair question, right? If this attention thing is so good at finding relationships, why make things more complicated? Well, this slide just nails the reason why. A single attention head would be trying to learn everything at once: grammar, meaning, who did what to whom, and it would just end up with a kind of muddled average. Multi-head attention, though, is more like having a committee of specialists. Each head can learn to focus on a different type of relationship. So the model runs several of these attention mechanisms all at the same time, in parallel. The original paper used 8 of them, and each head learns to pay attention to different things. Maybe one gets really good at tracking pronouns, while another focuses on verb-object relationships. The model then just combines all these different perspectives to create a far richer, more nuanced understanding of the sentence as a whole. Okay, but when you throw out the old sequential method, you actually create 2 brand new problems for yourself. How does the model know the order of the words? And how does it avoid losing the original information in a really deep network? Exactly. I mean, if you're processing everything all at once, the sentence, "the dog bit the man," has the exact same words as the man but the dog. Word order is absolutely critical for meaning, and we just got rid of the very mechanism that used to track it. The solution is actually pretty clever and surprisingly simple. You just add the position. Before anything else even happens, the model adds a special vector to each word that uniquely tells it where it is in the sequence. It's like giving every single word its own GPS coordinate, so the model always knows where it is relative to everything else. And here's that second problem. Transformers stack these attention layers one on top of the other, sometimes dozens of times. As information passes through all these complex transformations, there's a real risk that the original vital signal gets distorted or even lost completely. The fix for this is another elegantly simple idea: residual connections. You can think of these as information shortcuts or express lanes.
After a layer does its complex processing, this connection just adds the original, untouched input right back in. This makes sure that even in a super deep network, the model never loses the raw information from the layers below. So let's put it all together. We have multi-head attention to understand context, positional encodings for order, and residual connections for memory. And when you combine all of that, you unlock the single biggest advantage of the transformer architecture. This table, right from the paper, gets to the absolute heart of the breakthrough. For an RNN, the number of sequential operations is O of n. That means it's directly proportional to the length of the sentence. Longer sentence, longer processing time, period. But now look at self-attention. It's O of 1, a constant number of operations. It doesn't matter how long the sentence is.
This one little term, O of 1, is why everything changed. Because the main computation doesn't depend on the length of the sequence anymore. You can do it all at once. It allows for massive, unprecedented parallelization. You can process every word simultaneously, which is an absolute dream come true for modern hardware like GPUs.
And the impact was just staggering. Training times didn't just get a little better, they plummeted. Models could suddenly handle much, much longer texts. This incredible efficiency is what allowed researchers to scale up to the massive billion-parameter models like GPT-4 and all the others that we have today. The transformer didn't just improve on the old methods, it unlocked a completely new scale for AI.
And this leaves us with a pretty fascinating final thought. The paper made this huge claim for language, and it absolutely delivered. But the core idea of attention, of selectively focusing on the most relevant bits of information, that's a universal concept. So it makes you wonder, what other complex problems in science or art or anything else could be cracked if we just figured out the right way to pay attention?